Right, yeah.
Okay, so let's get started. Welcome everybody. I hope you enjoyed the midterm. Can you read this sentence? Yeah. No?
Because we're saying you enjoyed the midterm. Yes. As a teacher.
No. Me. How about that? Okay. So, this recitation will be on del, bounds, and averages. And before we go into that, let's just discuss why we are doing this. So, can machine learning work? And I think, you have already registered in the course, you're doing projects, stuff like that, so you already know that machine learning does work. Otherwise, life would have been much different. Like no Google, no spam filters, no midterm. But will machine learning always work? If I give you any data set with any labeling scheme, will you be able to learn the labeling scheme from the data set? And the answer is no. So this is an example. So these squares belong to class 1, the lower ones belong to class 2, and I give you two other squares and I ask you to classify them. So one might think, for example, maybe the reddish ones should belong to class 2 and the bluish one should belong to class 1. That's one possible answer. Another answer could be, well, no, dark colors should belong to class 2 and like bright colors or light colors should belong to class 1. And so you get opposite answers based on the labeling scheme. And the point is, I can devise any labeling scheme so that no matter, so suppose that, for example, we have discrete features, and so we have the number of possible data points is finite. Let's call it n. Suppose I give you n minus 1 training examples, and I ask you to predict the nth training example. There are two possible answers. One might have a labeling scheme where the nth training example is class 1, or a labeling scheme where the nth training example is class 2. And so the no free lunch theorem tells us that if all labeling schemes, if all true functions are equally likely, then there's just no point of machine learning, because no classifier will be better than the other on average. But we don't assume that. We assume that some functions are more likely than the others. We assume some regularity conditions. So for example, we assume that labels are somehow smooth with respect to features. So if 2 points have similar features, we expect them to have similar labels. We expect features to be somehow settable in maybe some high-dimensional feature space, and that sort of thing. So these assumptions are the assumptions that enable machine learning to work. And I actually know a group of people who don't like machine learning to work. You know them? No. Well, spammers don't like machine learning to work, but they have nothing to do about it. Yeah, I know, but there are people, they are not evil people, but these people have enmity with machine learning. There are people working in cryptography. So people working in cryptography, it couldn't be be nice if I am able to use machine learning techniques to analyze some encrypted text and corresponding plain text and come up with the encryption algorithm and security keys and that sort of thing. It would be nice to be able to infer these things using machine learning, right? I mean, a lot of things would collapse, like bank transactions and that stuff. So yeah, there's a kind of eternal enmity between cryptography and machine learning. So we like things to be regular and smooth. They like things to have what's called avalanche effect. Like if you change a single bit of the input, the output must drastically change. So far we've been like using our intuition to understand why algorithms work. But it seems that we need some theory to analyze machine learning algorithms in a rigorous manner. And so what we are going to do in this recitation is that we will go through the basic tools used to build this theory. And we will focus on estimating data, estimating averages. So we have data coming from some distribution. We estimate the sample average or the empirical average. How good is the empirical average as an estimate to the true mean of the distribution? And how does it converge to the true distribution as we get more and more data? So that's like the reason or the motivation behind this recitation. First, we will have an example because we are talking about estimating stuff. And then we will consider the topic of convergence of averages. Does the empirical average correspond to the true mean? And then we will consider inequalities and state bounds. And these inequalities answer the question like, how likely it is for my estimate to be far away from the true value? And how does this probability change as I estimate for more and more data? Then, depending on time, we might or might not discuss some tools used for proving theories. So, estimating probabilities. And let's consider a simple example, the discrete distribution. So, or the multinomial distribution. So, for example, you throw a die, and you get one of 6 faces. And the probability of getting the ith face is 5i. And so the data likelihood, so you throw the die and you get n1, you get face 1 n1 times, you get face 2 n2 times, and so on. And so the likelihood of the data, the probability of getting the data given phi is just the multiplication of pi I to the power ni. Is that unclear? Okay. So we want to do maximum likelihood estimation. So the parameter of our model is pi I, right? And we can do MLE the way we did for linear regression. But this is a constrained optimization problem. Why? So if you want to estimate pi, if you want to find pi that maximizes the likelihood of the data, so we will maximize this quantity subject to some constraints, right? What are these constraints?
It has to correspond to the probability distribution.
Yeah, phi I has to form a probability distribution. That means each phi I has to be greater than or equal to 0, and they have to sum to 1. And so you can solve that as a constrained optimization problem. compute the constraints, add Lagrange multipliers, and so on. Or you can use a trick, which is you simply write each pi I to be exponential theta I over the sum of all exponentials. So that will require each theta I to be greater than 0 because it's an exponential of something divided by a positive quantity. And it will force them to sum to 1 because you are dividing by the sum of the exponentials. Okay? Hey, once you do that and take the derivatives, maximize. So this is a nice trick to convert these type of constraints to an unconstrained problem. Once you do that and take the derivatives, you can find easily that theta I is the log of the number of times you see the I face divided by the total number of flows. And that means pi I is just the number of times you see the I face divided by the total number of flows. And this is the intuitive estimate that we know, maybe from high school or earlier, that like if you want to estimate the probability of getting phase 3, you just count the number of times you have seen phase 3 and divide it by the number of times you have thrown the die. Okay? Good. In practice, we can throw an unbiased die, so each phase should have equal probability. Each phase should be equally probable. But if you throw your die for a low number of times, like 12 times, you might not get uniform counts. You might get something like this. For example, you might get phase 2 will never appear. But that's not an accurate estimate, right? We know that the die is unbiased. So is it possible or is it probable to get something like this? And the answer is yes. If you do the math and you compute the probability of getting phase 2 0 times out of 12 throws, it will be 5 over 6 to the power 12, right? And so it's not an unnegligible probability. It can happen. But as you throw the die more times, counts begin to become more uniform and more truthful to the true distribution. So you get something like this, and like after 60 throws, you get something like this. And after 120 throws, you get something like this. So the more you throw the die, the more uniform the count gets, and the more accurate your estimates become. And if we scale that to, for example, 1,000 trials, we see that in the beginning, the counts are not uniform. And your estimates may not be very accurate. And if you compute the average value of the die, which would be 3.5 because we have values uniform between 1 and 6, right? If we try to compute the average value, it will be somewhat far from the true value. But as we increase our trials more and more, we get uniform counts, and the average converges to the true mean, or the true average. And the question is this convergence a guaranteed behavior if we repeat our trials more and more and more? Is that guaranteed to happen? And how quickly does it happen? So that would be our first issue, convergence of empirical averages. Just a reminder and an illustration of the notation notation we are going to use. You know that if f of x is, if x is a continuous random variable, and we want to compute the expectation of some function of x, we integrate f of x times p of x dx, right? What I'm doing here is a notation from measure theory, and this notation basically, roughly speaking, means if x is a continuous random variable, you just do integration f of x times px times dx. If f of x is a discrete random variable, then you are doing the summation. So this is a nice way if you want to prove stuff about probability. You don't want to prove a particular, you don't want to prove things twice, once for continuous random variables and once for discrete random variables. And some variables can be neither continuous or discrete. And so this is like a general way. This is a general way to express expectation regardless of the nature of the random variable. Okay. So, for example, this also something you should be aware of. The probability of an event is the expectation of an indicator variable that's 1 if this, if and only if this event occurs. So suppose that we have an indicator variable here that's equal to 1 if and only if x is equal to c. Then the expectation of this indicator variable is the probability of that event, which is computed again using this formula. And of course it works for intervals, so it can be x within some interval other than x is equal to a particular value. By the way, if x is a continuous random variable, what's the probability that, for example, if x is a Gaussian, what's the probability that x is equal to 0? 0. That's true. We'll assume that we have a distribution from which we draw independent samples, and we compute the empirical average. So the empirical average of f of x is just the sample average. And the empirical, as we said, the probability of an event is the average of the indicator variable corresponding to that event. So we can do that also on the empirical level. So the empirical probability that some event occurs is just the ratio of samples in which this event occurs. Okay? So the first convergence result is called the law of large numbers. Basically says if you sample your data from a distribution with mean mu, then the empirical average, and the empirical average denoted by this mu n hat, so this will be used throughout the presentation as the empirical average. The weak law of large numbers says as you get more and more data, so as your data goes to infinity, the probability that you deviate from the true mean by amount epsilon, so the probability that you deviate from the true distribution by amount no more than epsilon will go to 1 for any epsilon. So, for example, for epsilon, so this is the true mean. This is mu minus epsilon and mu plus epsilon. So the law says that as you get more and more data, in the limit, the probability that you stay within this interval will become 1. And you can make this interval as narrow as you want. this is called convergence in probability. There's actually a stronger result called the strong law of large numbers, and it says the probability that the limit of your empirical average is equal to the true mean is equal to 1. So this is the limit of the probability, this is the probability of the limit. This is a stronger condition, so this convergence implies this convergence. The distinction between them is somewhat technical and beyond this scope. But you just need to know that the empirical average converges to the true mean almost surely, which implies that it converges to probability. So, if we run our experiment multiple times, so here we have like 5 runs, and in each run, the empirical average of the value of the right finally converges to the true average. Okay? This clear? So now we know that the empirical average converges to the true average if it exists. We'll see examples that doesn't. But we didn't know yet how fast it converges. And so here comes the central limit theorem. So the central limit theorem gives you like more information about how these conversions behave, about this convergence behavior. So this is the general formula. It basically says if you center your random variables by subtracting the mean and divide by the square root of total of the sum of variances, then you get a Gaussian random variable. The interesting case is, well, all variables have the same distribution. So if all variables have the same distribution, then just ui is identical, and this becomes n sigma. This becomes n sigma squared. You multiply by root n and divide, you get this formula. So this becomes the empirical. This is the empirical mean. So the empirical mean minus the true mean multiplied by this quantity is a Gaussian random variable. The informal way to write it is that the difference between the empirical mean
Well, it's not showing up.
Yeah, I'll just use. So the difference between the empirical mean and the true mean is a Gaussian 0 and variance sigma over squared. It's an informal way because we are talking about things happening as n goes to infinity. And so we don't want the right-hand side to contain m. Right? But it kind of illustrates the idea that your error is getting narrower and narrower and narrower. Because as n increases, the variance becomes less and less.
So the first xi is the ground up, is the mean for the ith random variable, right?
Yeah, but here, okay, xi is the ith random variable. Is the ith sample. Okay? So it's a sample from the ith random variable. But then we assume that all random variables have the same mean and the same sigma. Okay? And this, some people, well, this is called O n to the power minus half conversions. The statisticians like to write it as OP n to the power minus half. And it's called this way because this is the quantity you are talking about. When you multiply it, that's if you divide by this, in other words, you multiply by root n, you still get a distribution that can be bounded, in the sense that you can say you won't exceed, for example, give me a probability, I will give you some value that you can't exceed this probability. So this is a demonstration of the central limit theorem. We keep adding variables of uniform distribution. So this is the sum. This is the average. And as you can see, so one variable will have a flat distribution. Two variables will have the convolution of two flat distributions, so it will be triangle. And as you add more and more variables, you get closer to a Gaussian distribution. And if we add more, we will notice that the variance of this Gaussian distribution becomes null. Okay? Okay, cool. So now I've seen how well empirical averages converge. Yes?
On the previous slide, the sums from 1 to n, is n the number of data points?
Yeah.
So each data point has a mean and standard deviation?
Yes. So this is like the general formulation, and here we assume that each data point comes from the same distribution. So you have the same mu and the same sigma.
Should that vary with this environmental level? Should it be square, sigma square over?
Yeah, I'm writing the standard deviation. So the variance would be, yeah, so this is the standard deviation. The variance would be 0 sigma squared over your length. Okay? And so now we will go to the second issue, air bounds. Again, the basically answer the issue of how likely can I estimate things better? How likely can I go very far away from the two values? Okay. So we will go through a sequence of bounds. Each equation provides the tighter bound, that means the better results. And we will see what better means. Basically means that you will need less data to achieve the results you want, to guarantee the results you want, I would say. But at the same time, they assume more assumptions. So as we go, we'll have better results, but more assumptions. Okay. The simplest step bound is Gauss multiple inequality, or we can call it just multiple inequality. It basically says if your variable is non-negative and it has a mean mu, then so you have maybe a distribution like this. And you want to estimate the probability of being greater than some epsilon. And the inequality states that this probability is less than or equal to over epsilon. So decreases linearly with the inverse of epsilon. The proof is quite easy. The probability that x is greater than or equal epsilon is you just integrate over the probability measure, And again, that means integration for continuous variables and summation for discrete variables. Starting from epsilon to infinity. But about epsilon, the x over epsilon will be greater than 1. And so this is an upper bound of this one. So we can move epsilon outside. And this is an integration from epsilon to infinity, so it will be less than integration from 0 to infinity, right? And this is nothing but the mean. Okay? This is the simplest state bound. A nice tail bound is called Chebyshev inequality. And in this case, we assume, we don't assume that the variable is non-negative, but we assume that the variance is finite. And so what the inequality says is that the probability that the empirical mean deviates from the true mean by an amount more than epsilon is less than or equal sigma squared m minus 1 epsilon minus 2. So m is the number of points for which you estimated the empirical mean. You can prove this easily, but if you just square everything, so if you square mu m hat minus mu, that becomes a non-negative random variable. You apply Markov inequality, you get this result. So this basically tells you, as you increase the data, the probability that you overshoot or undershoot the true value by an amount more than epsilon decreases as you increase more data. It also tells you that this probability, if your variance, as your variance gets higher, your bound gets higher, right? We want this bound to be as low as possible, right? I mean, this is the probability of being wrong, and we will call it delta. So delta is the probability of being wrong. We want this probability to be low, and we see that this probability increases with the variance, which kind of makes sense. It also increases with the inverse of epsilon squared. And so as you want higher and higher accuracy, your probability of being wrong increases with that. We can also, so this delta, we can write the same equation this way. And the question is, does this equation provide us some guarantee of being correct? So what does being correct, exactly correct, mean? Which variable has to be changed to say that we are exactly correct? Well, it's epsilon. If we set epsilon to 0, right, that means we are basically, delta becomes the probability of being unequal to mu by whatever quantity. We don't care. So if we set epsilon to 0, then we are talking about being exactly correct. And now, can we be exactly correct? The right-hand side clearly says no, because the right-hand side will become infinity. Right? So you can't be correct. And so, since epsilon is greater than 0, you can only be approximately correct. So can we be do we have a guarantee of being approximately correct, at least? That is staying with an interval of mu minus lambda to mu plus lambda? And again, the answer is no. Because we want delta to be 0, right? To be always approximately correct, we want delta to be 0. But sigma squared is not 0. Epsilon minus 1 squared is not 0. And so our only hope is to get infinite data. And so as long as you have finite data, no matter how many they are, as long as they are finite, you can only be probably approximately correct. Probably means you have epsilon greater than 0. Probably means you have delta greater than 0. Approximately means that you have epsilon greater than 0. Okay? And I think many of you heard this term, probably approximately correct, or packed learning. So packed learning theory is based on this concept that you can only be probably approximately correct. And so we might say, okay, now we have an inequality from which you can build a packed learning theory. But the point is, this inequality provides full scaling probabilities. This inequality provides full scaling probabilities. We want epsilon to scale better with delta. So we can see a kind of trade-off between epsilon and delta, right? Basically, if you want to be more accurate, you need to you need delta to be higher, and that means you are somehow tolerant with respect to being confident of being correct. And at the same time, if you want high confidence of being approximately correct, then your approximation has to be wider. So let's see the two inequalities we have just discussed. So Gauss-Markov said that epsilon is less than or equal to mu over delta. So this one scales property in mu, but expensive in delta. It scales with 1 over delta. Remember, epsilon and delta are less than 1, and we want them to get really close to 0. And so dividing over by epsilon is a very large quantity. For Chebyshev, we get this. Well, first, like the bond decreases with the amount of data, which is good. But it's still 1 over root delta, which is not that good. We want a logarithmic scaling in delta. Why? Because we will see that in class that we would like, so for example, suppose that we want delta to be 0.1. We want to be approximately correct with probability 0.1 of being of error. In the actual scenario, to get this probability, we are talking about being wrong in a single experiment. But in reality, we want to be correct in multiple experiments. And so we need to multiply delta by something. And so we don't want, so if you want to multiply delta by something and that scales you epsilon by the same amount, that's not a good thing. And so we want epsilon to scale with the log of delta. So that we need to multiply, when we need to multiply delta by some amount, epsilon does not scale by that amount. And we don't see that in details in class, but the point here is that we want epsilon, this scaling is not good enough. Okay? So let's try finding a better inequality. And fortunately, there's a good one, and it's called Chernoff bound. So if you have Bernoulli random variables, and the probability that x equal to 1 is equal to b, and you know n data points from that Bernoulli, so for example, you toss a biased coin n times, then the probability that you deviate from the that your weighted average deviates from the two mean by amount epsilon in the positive direction. So there is no absolute value here. Now we are getting exponential minus 2n epsilon squared. So here we're talking about 1 over epsilon squared. Here we're talking about exponential of minus n epsilon squared, which you can see provides much faster decay in your error as you increase n. We will go quickly through the proofs. So to prove this thing, we need to show, we will introduce an intermediate quantity, and basically we will show that this inequality holds. And this inequality is like a very, I already know the result for Twin-Squares inequality, so we'll not prove it here. So we'll care about this one. So what is P and Q? So I'm saying, so remember, our original statement was mu n hat minus P is greater than or equal epsilon, right? And assume that Q minus P is equal epsilon, then this means the probability of sigma xi over n minus p is greater than or equal Q minus p. And this immediately gives this. So this is the left-hand side of our inequality. And this one is the right-hand side. So this exponential minus 2n epsilon squared. Yeah?
Change the first one.
Yeah, this is like a removing the piece. Okay? So this is the same inequality. We just introduced this intermediate term. And this intermediate term is the KL divergence between the Bernoulli distributions parameterized by P and Q. So the KL divergence is a measure of how far two distributions are. And for Bernoulli distributions, the formula is simple. Okay? And then the idea of the proof is that you apply like a sequence of tricks, basically that the probability is less than 1. So I won't go in detail. I will just basically illustrate things so that you can read the proof, by yourself. So this is the we basically compute this ratio, and so this ratio depends basically on Q for the upper one and P on the lower one. So this is the probability that you get exactly K successes out of n trials. So this is a well-known formula, and then assuming that Q is greater than P, you can exploit the fact that this is greater than 1 and this is less than 1. And so as you increase this exponential and decrease this exponential, you get a higher number. And many of you were not aware of that on the midterms. So on the regularization question, when you have a loss function to the power 4, many of you said the loss function to the power 4 increases all errors It doesn't increase all errors, and that's why it fits to the outliers. It increases only large errors, errors greater than 1. Because if you have x less than 1, x to the power 4 is less than x to the power 2. And so the same thing here. You are increasing this exponential and decreasing this exponential, but this ratio is greater than 1, this ratio is less than 1. So you get a higher number than this one. And you can easily show that this is the exponential of this expression. Once you do that, you have the ratio, so you have probability of getting k successes given q in terms of this one. And so you just substitute here and do the summation, and then use the fact that any probability is less than or equal to 1 to move this factor. But, I mean, anyhow, don't worry if you don't get the proof now. You just go through it slowly and you'll find it easy. The point is the inequality itself. So we assume that xi are denoted under variables, but in general, if xi have bounded range, so xi is between minus c and c, we get what's called Hofting inequality. And I would say this is like one of the basic pillars of computational learning theory, in back learning modeling especially. So the probability of being of not being approximately correct is less than or equal to this exponential. So we have exponential decay over the number of examples, and exponential decay as you become tolerant to new approximation. And now, so remember we were looking for epsilon, how epsilon scales with delta. Now we get the log scale we're talking about. So rather than scaling with 1 over root delta, now we're scaling with just root delta. Okay? By just taking the log of both sides. And again, we will see that we want to combine the probability of, we want to combine this inequality for multiple experiments or multiple classifiers or whatever, and so we don't want epsilon to scale with the amount of delta, because we want delta to be multiplied by something. Okay? So the following two items are not as important as Hofting's inequality. So they are just, so this is a nice generalization of Hofting's inequality. It might look unpleasant, but it's really not that complicated. So this is a generalization. So for Hofting inequality, we're talking about empirical average and true mean, right? Here, this is a generalization where we are computing just an arbitrary function of the samples, and we are comparing it to the expectation of that function. And what the inequality says is that we get similar behaviors. We get like exponential decay in epsilon squared. What is this C? Basically, so we have a function of m variables, and C is determined by how much can you change the function by changing only one variable. So you compute that for each variable and sum. If we go back to the Hofting's case, So f is the empirical average. So f is equal to sigma xi over n, right? What's the maximum amount I can change f by changing one variable, given that x is between minus c and c? So if I, for example, suppose I allow you to change x1 eventually, what amount of change can you cause to f by changing x1? C over m, right? So the maximum change is just C over m. And so if we sum the squares, we get n times C over n squared, right? Which is equal to C squared over m. You just substitute that here, and you get Hopkins inequality back. Okay? There are more inequalities. I mean, we can talk about that topic forever. So, for example, if you assume, we assume that our samples are bounded. So we assume that x is between minus c and c. But we didn't tell, for example, whether they are uniform between minus c and c, or they are something like this. Still between minus c and c, but with less variance. Hopkins inequality doesn't make use of this explanation, but if you can bound the variance, you can expect to get better bounds. And so, for instance, the equality, for example, tells you if you know the variance or know an upper bound on, the second moment, which is related to the variance, if you know that or know an upper bound there, you can use that to get better convergence results. Okay, and you can find again, like if you assume, so if you assume weak dependence between random variables, you can get better bounds for that, and so on. Okay, so far we have went through a sequence of inequalities, and the basic idea was. The question was, I'm estimating the stuff from data. How likely am I to be wrong? Right? So we found that I can bound this probability somehow, but I need some assumptions. And to get better bounds, I need more assumptions. So we started with the Markov equality, which just assumes that the real variable is non-negative, and that's it. But it provides very poor bound. This bound does not even change as you get more data. And then we discussed Chirchev equality, which has sort of assumption. The variables can be negative, but they have to have finite variance. And when discussing Chirchev inequality, we discussed the concept of being probably approximately correct. So you cannot ensure being correct, exactly correct. You have to have some error margin epsilon greater than 0, and you can't guarantee being approximately correct with probability 1, because you have to have some probability of error delta greater than 0. And then we found that if you don't just assume finite variance, but assume finite range, so your variables are between minus c and c, you get even better results, and you get a kind of exponential decay in your error bound. And as you add more assumptions, you can get better and better bounds. So why do you want tight assumptions? So the let's consider, for example, this case. Yeah, let's consider this case. So epsilon is less than or equals sigma over square root u delta. That gives you u delta is less than or equal sigma over epsilon. You square the thing, so you get mu is less than or equal sigma squared over delta epsilon squared. So that means if I tell you that I want to estimate the empirical average such that I want the error to be less than 0.1 or 0.01. Again, you can't ensure that to happen. So I want that to happen only with, I want the error to exceed 0.01 only with probability no more than 0.01, for example. Now you can estimate the number of data points that you can estimate an upper bound of the number of data points that you need to satisfy this requirement. As if we get better bounds, we get lower, you get basically lower values for x. So you declare that, well, I don't need that much data point, I need something less. And that's good, right? I mean, knowing that you need less data to do your job is, yeah, it's a good thing. Okay? So this was like the bulk of the recitation, the core part. In the remaining time, we will go through some tools that you can use to prove theorems regarding conversions and probability statements and that sort of thing.
So for the Chebyshev bounds, we're assuming finite variance.
Yeah.
So isn't what variance always finite? Like for finite number of data points, doesn't we have some?
No. So we assume finite values of the true distribution, not the sample values. Yeah, good question. So the question was, what do you mean by assuming finite variance? Like the sample variance is always finite. We are talking about finite variance that the distribution for which you sample the data has finite variance. Some distribution doesn't have finite variance. Some distribution doesn't have even a defined mean, like the Cauchy distribution. Okay. Any questions on anything said before we continue?
So we have mu hat, but we just have sigma, versus assuming we have the same deviation.
Yeah, so sigma is the true standard deviation. You don't know it, that's true. But for example, we care about like the rate of conversions, sigma squared is just a constant. So this is like what you do in algorithm analysis, right? You don't know, for example, how long does multiplication take in nanoseconds. And you don't really care about that. You just care how does the computational time grow with inputs, right? That's what you do in complexity analysis or when you analyze algorithms. The same thing here. Right? I mean, we don't care much about the constants. We care about like the behavior, like how delta change with epsilon, how the number of data points changes as epsilon and delta change, and so on. So yeah, it's unknown, but it's a constant. Now, mu height changed based on the data, so you have a fixed distribution with fixed mu and fixed sigma.
Yeah, but if we don't know mu, we don't know sigma.
Yeah, you don't know if that's true, but when you analyze your estimation, you analyze basically how your estimation gets better as you get more data. Again, it's like in algorithm analysis, you analyze how your computational time gets more as your input gets larger. There are some constants, right? But you care more about rate of growth. So it's a similar concept here. We don't know sigma squared. So we know that as sigma squared gets higher, basically we need more data. That's true. But the fact that we don't know sigma doesn't make this kind of analysis useless because it still gives us the rate of growth.
No, that's good.
Okay, I mean, we can discuss it. Okay, the first tool, and it's a simple one, it's like, though its simplicity, you can be amazed by how widely used it is. The union bound, it relies on the simple probability fact that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection. And that's less than or equal to probability of A plus probability of B. So in general, when we have a number of events and we want the probability that at least one of them happens. So for example, the probability that I made at least one error in the sense of being approximately correct is less than or equal to the summation of probabilities of those events. And you can easily see it does not provide you a tight bound because it assumes an untypical condition that there is absolutely no overlap. I mean, for this inequality to become equality, there has to be absolutely no overlap between events. Which, I mean, sometimes the analysis is more complicated when you try to incorporate overlaps. So it simplifies the analysis, but does not provide like the tightest bounds you can go. And I would say union bound is this maybe the second key ingredient in fact theory. Fourier transform. So if you have background on signal processing, communication, stuff like that, you have probably encountered Fourier transform. How many of you doesn't know Fourier transform? Okay. So you haven't heard about it, or you kind of like don't remember the exact formulation and that stuff? Okay. So this basically, if you have a signal, then you have some function over time, right? And looking at the function, this function over time might not be that insightful. And so you assume that this signal is the superposition of different signals at different frequencies. So we can say that this signal, for example, is the result of some no changing signals. Okay, let me plot it. Okay, so this is the original signal. Maybe something like this. Basically, it can be the result of a low frequency signal and in a high frequency. Kind of basically Fourier transform is a transformation that you apply to such a signal. And so you get the signal as a function of frequency rather than time. And so for something like this, you can get like you can get something like, so for a single sine wave, for example, you'll get just like a single frequency. So this corresponds to like a single sinusoidal signal. And like for a composite signal, you can get like multiple frequencies, and you can get like an entire spectrum of frequencies. Okay? And so, for example, if you have if you have two wireless communication channels, at either like one of them at 2.4 gigahertz and another at, I don't know, maybe 3 gigahertz, then just looking at the time domain will give you something like this. You'll have a superposition of two signals. But looking at the frequency domain will give you something like this. So you'll basically see how these two signals, which are superimposed in the time domain, how they are kind of decomposed in the frequency domain. Okay? This transformation is unique, so it's like preserves all information in the sense that there's an inverse transform, and if you apply the inverse transform, you get back your signal. Okay? Also, a nice thing is that the Fourier transform of the derivative of f is minus iw, the Fourier transform of f. So the derivative becomes as easy as multiplying by w in the frequency domain. Convolution becomes just multiplying the two signals. So are you familiar with like the concept of convolution?
Is it the composition? That's the composition of two functions, right?
Yeah, so this is the Fourier transform of f convolved with g. Okay, so so the conclusion is, like in mathematical terms, f convolved with g at time t is equal to the integration of tau from minus infinity to infinity, f of tau, g of u minus tau, d tau. This is like the mathematical definition of the term. But like to see what it means. Suppose, for example, we have something like, so this is f of t, and this is g of t, just an arbitrary function. So if we compute the convolution of these two functions, so what's the evaluation of this integral? And so what's f of g, for example, at 1? Well, f of t is 0 everywhere, right? Except at 3 when we have an impulse, right? And so it will become just g of t minus 3, right? Because that's the only case where f of t is non-zero and it has like an impulse, right? And so the convolution basically tells you what's the output of a system, basically whose response function is specified by f of t if you input g of t to that system. So in this case, the output will be that they're just you're basically delaying the signal. So the output at time 1 will be g of minus 2. The output at time t in general will be g of t minus 2. This is like one interpretation of convolution, but in probability, convolution has the mathematical meaning of convolution would be of interest. So remember we said f convolved by g times t is equal to the integration of tau, f of tau, g of t minus tau, d tau, right? Now, suppose I have two probability distribution, two independent random variables, and f of x is the PDF of the first random variable, g of y is the PDF of the second random variable, and I want to compute the PDF of their sum. Let's call it h of z, right? So h of z, the PDF as z would be, I need to take all combinations of x and y that sum to z. And so that gives me integration over x, f of x, g of z minus x, dx. Does that make sense? So think of it in discrete case, where we have just summation over x, the probability that x is summation over I. think of it in the discrete case. The probability that z equals j is equal to the summation over I, and basically you sum all possible combinations of x and y that sum up to j. And so you convolve the PDFs of x and y. And since we have a method to convert convolution into multiplication, we can apply that to PDFs. And so if we apply the Fourier transform to PDFs, we get something that's unique, preserves the uniquely identifiable distribution, and easy to convolve. And that's what's called the characteristic function. So the characteristic function is just, some people write it this way. So some people just write it as the expectation of e to the power I omega x. But this is just the inverse Fourier transform of the PDF. And again, if you want the joint, if you want the distribution of the sum of two independent linear variables, because it's convolution, you can compute it from the characteristic function as a product. And remember, we used to sum independent linear variables to compute the empirical average, right? And so we can use that to basically prove things like the weak law of large numbers and the central limit theorem. I'm not going through the proofs now for time constraints, but the idea is that you deal with the characteristic function, and that becomes the sum of xi's becomes basically you multiply the characteristic function by itself m times. It becomes very easy to prove things instead of doing convolution integral m times. So that's the end of the recitation. We looked at the basic building blocks that's used to build the learning theory. We looked at conversions of empirical averages, create bounds, and union bound. I would say the later two are like basic ingredients. So now, if we evaluate a classifier on n data points and estimate accuracy, can we upper bound the error in our estimation? So maybe the accuracy of the classifier is like 70%, but we evaluated them 100 data points and say no, the accuracy is like 65%. So there will be some error in our estimation. Can we upper bound that error? And the answer is yes, because we know how to deal with the nonlinear variables using Chernoff bound to solve this inequality. We can say that we are probably approximately correct regarding our estimation. But in reality, we don't have one classifier. We have a set of classifiers. And so we want to be approximately correct, probably approximately correct on all of them. So we'll use the union bound. But then a problem will arise. We don't have like finite number of classifiers. So for example, you do something like logistic regression or any linear classifier, you have a number of parameters that are real. So the number of classifiers you can build is infinite actually. And so just using the union bound won't work. It will give you, the probability is bounded by infinity, which is not that helpful, right? And so the next step, which you'll see in class, is that we will need a measure of complexity of our classifiers. We can't just say the complexity of logistic regression is measured by the possible number of linear classifiers. That won't work. So that will delve us into things like VC dimension and that sort of things that you may have heard about. Okay?